Good day to my final year project supervisor Dr. Devagi, our course coordinator, and my examiner Madam Amira, and also to everyone. My name is Felicia Elisa Nagai, and my matrix number is 65976. I would like to present my final year project thesis entitled Synthesis of Titanium Dioxide coupled with zinc sulfide for the removal of methylene blue. I would like to begin my presentation with introduction of my project, which consists of research background, problem statement, and lastly, research objectives. The first part is research background. For this study, titanium dioxide zinc sulfide photocatalyst was used to degrade methylene blue. Titanium dioxide is a semiconductor with a UV bandgap and transparent visible area, making it useful in photocatalytic activities such as organic pollutant degradation. Titanium dioxide photocatalysis is also known as one of the most significant photocatalysts due to its remarkable photocatalytic effectiveness, ease of availability, long-term stability, and non-toxicity. As for zinc sulfide, it has been used to degrade organic pollutant molecules because of its photoactivity, stability, and non-toxicity too. Next, hydrothermal method is used in this study for the synthesis of titanium dioxide zinc sulfide, and it also has been applied widely for the preparation of titanium dioxide-based composites. In this study, methylene blue is a cationic dye that has chosen as the model pollutant. Various conventional methods such as physical, chemical, and biological techniques have been tried to extract dyes from aquatic media. The problem statement in this study are titanium dioxide is efficient photocatalyst, but it has several limitations such as titanium dioxide small bandgap and only active under light. Thus, to overcome these limitations, titanium dioxide can be combined with other materials. Besides, zinc sulfide has been chosen due to its photoactivity, stability, and non-toxicity. The research objective of this study are to synthesize the titanium dioxide zinc sulfide by a hydrothermal method, characterize the titanium dioxide zinc sulfide photocatalyst for its surface morphology and chemical structure, and lastly, to investigate the efficiency of titanium dioxide zinc sulfide photocatalyst for the removal of dimethylene blue. Moving on to the methodology part, in this study, the methods are consist of preparation of zinc sulfide, synthesis of titanium dioxide zinc sulfide photocatalyst, characterization of titanium dioxide zinc sulfide photocatalyst, preparation of stock solution, photocatalytic activity, and lastly, the effect of operational parameters. Firstly, preparation of zinc sulfide started by the preparation of zinc nitrate solution by dissolving of zinc nitrate hexahydrate in water. Next, sodium sulfate solution was prepared by dissolving sodium sulfide in water and continued with the mixture of zinc nitrate and sodium sulfide solution that was added together to form zinc sulfide precipitate. The second method is synthesis of titanium dioxide zinc sulfide photocatalyst via hydrothermal method. At the end of the synthesis, a white gel was produced. The solids prepared were approximately 0.2, 0.5, and 10% of zinc sulfate on titanium dioxide. Next is characterization of titanium dioxide zinc sulfide photocatalyst, where the surface morphology and chemical structure of the photocatalyst was analyzed by using scanning electron microscope, Fourier transform infrared spectroscopy (FTIR), energy dispersive X-ray spectroscopy (EDX), and transmission electron microscope (TEM). For the preparation of stock solution methylene blue powder was used to prepare 1000 ppm of methylene blue stock solution. The stock solution was diluted by using deionized water to prepare 2 until 10 times 10 to the power of -4 molar methylene blue stock solution. The next method was for the photocatalytic activity. UV lamp with length 365 nanometer and visible light was used to assess the photocatalytic activity of the titanium dioxide-based binary composite samples. Lastly, the concentration of methylene blue was analyzed using UV-V spectrophotometer with wavelength 664 nanometer. The percentage removal of methylene blue were calculated as shown in the formula. The last method is effect of the operational parameters, which consists of dopant concentration study, adsorbent dosage study, initial concentration study, and lastly, effect of pH value. Move on to the result and discussion. This chapter was divided into two parts, which are the characterization of titanium dioxide zinc sulfide photocatalyst and the effect of the operational parameters. Titanium dioxide zinc sulfide was characterized by using SEM, FTIR analysis, EDX analysis, and TEM analysis. The first one is SEM analysis, which the result was taken from Telvi et al. 2017. The morphological changes between titanium dioxide, zinc sulfide, and the titanium dioxide zinc sulfide heterostructure can be clearly seen in the SEM images. Figure A shows the SEM image of zinc sulfide which appear as bigger spherical particles. Meanwhile, B shows the SEM image of commercial titanium dioxide which have smaller spherical particles. Besides, figure C shows the flower-like zinc sulfide particles are observed to be perfectly deposited on titanium dioxide. The SEM images of titanium dioxide show that the particles are slightly aggregated, whereas titanium dioxide zinc sulfide image, figure C, shows that the particles are not aggregated. Hence, zinc sulfide modification preferably retarded the aggregation of titanium dioxide. Next is the result of FTIR analysis, which was also taken from Telby et al. 2017. FTIR analysis was done to compare the functional groups between commercial titanium dioxide and C, titanium dioxide, zinc sulfide photocatalyst. The sample shows minimal absorption when present for commercial titanium dioxide and titanium dioxide zinc sulfide photocatalyst. Meanwhile, FTIR spectra of B, zinc sulfide, showed the characteristic of zinc sulfide vibration peak. The third one is the result of EDX analysis taken from Dashamurthy et al. 2014. The presence of titanium, oxygen, zinc, and sulfide in the sample were clearly revealed in the figure confirming the identification of the titanium dioxide zinc sulfide photocatalyst. Lastly, results of TM analysis taken from Dashamurthy et al. 2014 and Franco et al. 2009. The TEM images of the left side shows the TEM image of titanium dioxide zinc sulfide photocatalyst in different magnifications, which are A 100 nanometer and B 200 nanometer. Based on the figure, the particle diameters range between 3 and 20 nanometer. Same size distribution and morphology of titanium dioxide zinc sulfide, where it appeared in spherical shape. Furthermore, the figure on the right hand side shows that electronic microscopy characterization revealed no significant changes in titanium dioxide morphology following zinc sulfide deposition. Next is the effect of operational parameters. The first one is effect of dopant concentration of titanium dioxide zinc sulfide. The dopant concentration was varied from 0.2, 0.5, and 10 weight%. In the presence of titanium dioxide, the full degradation of the methylene blue just took 90 minutes. Amongst these three dopant concentrations of titanium dioxide zinc sulfide photocatalyst, 0.2 weight% of titanium dioxide zinc sulfide outperformed the others in removing methylene blue solution. The second parameter is adsorbent dosage of titanium dioxide zinc sulfide. As you can see in the graph, the rate constant of degradation increased at 60 minutes when the catalyst concentration increased from 2 gram per liter until 6 gram per liter. The third one is effect of initial concentration of methylene blue. The graph shows that the rate constant of degradation reduced when the dye concentration increased from 2 to 6 times 10 to the power of negative 4 molar with constant loading 6 gram per liter. Lastly, the effect of pH value, which the result was taken from Franco et al. 2009. Based on the graph, the rate of deterioration was reported to be fastest in the solution of pH 10. Conversely, an intermediate adsorption condition was observed for neutral pH. A violet solid correlation was found in this experiment, which most likely linked to the dye protonation or deprotonation mechanism. In conclusion, the removal of methylene blue was successfully performed by using synthesized titanium dioxide zinc sulfide photocatalysts with different dopant concentration, namely 0.2, 0.5, and 10 weight%. The synthesized titanium dioxide zinc sulfide photocatalyst was characterized for its surface, morphologies, chemical structure. It also can be concluded that the removal of dye methylene blue using titanium dioxide zinc sulfide photocatalyst was efficient. As a recommendation, the photocatalytic degradation of methylene blue by using titanium dioxide zinc sulfide can potentially be used for the remediation of organic contaminants from wastewater. Last but not least, I would like to thank everyone for the support and contribution in completion of my final year project, especially to my final year supervisor, Dr. Devagi, my family, and also my friends. Thank you so much.